Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer those questions at the end and to follow up with any unanswered questions by email. As I think you all know, these Tech Talks have been designed to provide straightforward insights into radio frequency components. We talk about the related technologies and certainly about the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I am once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and numerous white papers and technical articles on passive microwave technologies, Shaun has been with Quantic TRM since the late 90s. And his passion for the job and for solving problems has only increased over the years, especially when it comes to resolving our customers' design and engineering challenges. So welcome, Shaun. Can you share an overview of today's topic and your objectives for the session?
Yeah, thank you, Paul. I'd love to. Really, what we're going to talk about today really are performance trade-offs that need to be made for most design endeavors. And really, we'll start by talking off really as to why these trade-offs need to be made, as to basically laws of physics and those sorts of things. We're then going to go in detail. We're going to go over some of the trade-offs that need to be made, talk about 90-degree hybrids and amplitude balance. Once from there, we'll then move on to some phase balance trades and phase shifters. We'll wrap it up with a summary, then finish it up with some Quantic TRM differentiators.
Okay, well, that sounds good. So to get started, why exactly is amplitude balancing so necessary?
Yeah, so now when you're talking about a 90-degree hybrid, a very important parameter for there is how balanced are the two outputs. And that is a key parameter for a hybrid, in addition to the fact that you're going to get a 90-degree phase shift. What's really important here to realize is that the amplitude balance of these structures are all based off of polynomials mathematically. And the way we realize those polynomials in real circuit descriptions is what we do is we take each one of those factors of the polynomial and it becomes a distributed element. Once you do that, what you end up with is essentially a bandpass structure. Within that bandpass structure, we now have the polynomial is configured to have an equal ripple response across any given bandwidth. And this is kind of what happens in the background as you're designing these parts that many people really don't realize is that there is an actual mathematical function that drives the equal ripple function across the operating band. As a result, what you get is that you have a couple of independent variables that drive this, and that is bandwidth, amplitude balance, and the number of sections are all interdependent on each other. And we're going to go through some examples of that in the upcoming slides. Bottom line, though, is if you change the bandwidth and you don't change the number of sections, you can go through there and you adjust and you vary the peak-to-peak performance. So the only way to get equal performance across a broader bandwidth is to add more sections. So what does that do for the overall circuit? Let's find out.
Well, I'll look forward to hearing these examples then.
So in the initial discussion here, what we have here are a 3-section hybrid. Each one of those traces on the screen is the mathematical result of a 3-section hybrid. And as a result, you can see that you have 3 equal ripple amplitude balances within the pass band. What's varying here is the bandwidth, and with the optimum number of equal ripple sections that you can get within that bandwidth. So the red diagram there shows a 2.5 to 1 bandwidth, and it has an amplitude unbalance of 0.1 dB, which is really quite excellent. If you need to expand the bandwidth from 2.5 to 4.5 bandwidth, you then move to the green trace, which now has an amplitude unbalance of 0.6 dB. Again, this is something that is probably not too unreasonable. However, you could see that the degradation that happens in amplitude balance as we open the bandwidth up. And of course, if we go to a much more extreme example of bandwidth of a 9.5 to 1 bandwidth, the black trace there, now we now have an amplitude unbalance of 2.1 dB on a 3 dB hybrid. And for most cases, this amplitude unbalance is going to be unacceptable for most applications. So part of the trade here, with what we're looking at here, is for all of these cases here, is that the physical size of the hybrid will be the same. They're all going to have the same 3 sections. They're all centered at the same center frequency. In this example here, 10 gigahertz, so that all these parts will have the same physical size and therefore the same insertion loss. So the trade-off that happens here with a hybrid that has 3 sections, but by increasing the bandwidth, the penalty that we're going to pay for that extra bandwidth is amplitude balance. So that is really the first thing, is that amplitude balance and bandwidth sort of go opposite each other. The wider the bandwidth, the larger the amplitude imbalance. And for many systems, there's a limit as to what that amplitude imbalance can be, which really limits the amount of bandwidth that you can get out of any one particular structure.
Okay, well, what happens then if there is some size variation?
So if we allow it to vary the size of the part or the number of sections, we can bring the amplitude balance back down to something along what we had with a narrowband part. So in the examples here, the red trace is a 9-section 9-degree hybrid. And with 9 sections over that same 9.5 to 1 bandwidth, we can get the ripple back down to 0.1 dB. Whereas with the 3-section example, the amplitude imbalance was 2.1 dB. A few things happen once you actually do this. First, yes, theoretically you can get the amplitude balance back down, but the penalty that you're paying here is that you've added a significant number of sections to the transformer, which is going to increase the physical size of the part as well as increasing the insertion loss of the part. Since these are distributed transformers, each one has copper losses and material losses associated with them, and the more sections that we add, the higher the loss is going to be. In addition to that, once you cross a threshold with an n-degree hybrid, you can no longer physically realize what mathematically is required. And we've done this now with this 9-section hybrid. The center section coupling is so strong, or what's mathematically required to be so strong, is we can no longer realize this as a single coupler set of coupled lines. We now have to go in there and actually fabricate this as a tandem hybrid, which is basically 2 hybrids running in series with each other. Therefore, once you do that, your insertion loss doubles automatically because the length doubles by going with that. I said you can get the amplitude balance performance out of it, but your insertion loss increases significantly. And in this case over here, the circuit length just got 6 times longer over the 3-section. So the insertion loss will be 6 times more with a 9-section than what we get out of a 3-section. Moving over to the next example here, this is saying here we don't necessarily have to increase the get the amplitude balance better by moving to having more sections. Sometimes if we just want to increase the bandwidth and maintain the same amplitude imbalance, we can accomplish the same thing here. The examples that are on the screen here right now is the black trace, which is the one that we've been talking about earlier, that has a 4.5 to 1 bandwidth, that has a 0.6 dB amplitude imbalance. This is fairly typical for what most specs are when we're designing hybrids. If we were to make a 9-section hybrid out of that, we can now increase the bandwidth up to 13.7 to 1, which is a really major increase in bandwidth. Again, this is going to have the same penalty as the previous example of having to go to a tandem hybrid to be able to realize these sorts of tighter coupling values that you need for these really high, very broadband, very high section count that happens when you get into these hybrids. And really going to these very broadband 90-degree hybrids, the fact that you have to move to a tandem is a major consideration. It doubles the physical size of the part, and like I said, since it doubles the physical size, even without increasing sections, you automatically double the insertion loss. So this is a major penalty that needs to be paid to get that additional bandwidth. And at this point, I think it's worth noting that if you really don't need all that extra bandwidth, that it very likely might be better off by specifying, 2 separate hybrids. Very often, system engineers will want to maintain, reduce the number of part numbers in a system. And the hybrid for any one location in the system will typically not need to operate over this entire bandwidth, as shown in this example here. Yet we have, but you may have 2 or 3 frequency bands in the system where you want to have, and very often it just kind of makes sense to, if we can reduce part numbers, to use the same part in various locations. Sometimes, like I said, from a performance standpoint, it really makes sense to specify 3 or 4 different hybrids in that case, where you want to go in there with a narrower band device, reduce sections, better performance, and then just use separate part numbers for the various locations in the system.
Okay, I guess that makes good sense. Now, I've also heard you speak of Schiffman phase shifters. What impact do they have?
Yeah, there's a similar sort of penalty when we go into looking at phase shifters as what we have for 90-degree hybrids. They're all based on distributed line transformers, and therefore the same sorts of penalties occur. The black trace on the screen here right now is a single section, sort of very typical octave sort of bandwidth. In this case over here, 2.3 to 1. Sort of performance. If you can tolerate plus or minus 4 degrees of phase variation or ripple. This is very often what most people use when they refer to these sorts of this type of a phase shifter. You can increase the bandwidth of the phase shifter, and if you take a look at the red trace there, that is a 3-section Schiffman design, and that goes up to a 5-to-1 bandwidth. Again, the penalty we pay here is higher insertion loss because the shifter has 2/3 more trace length in it in the actual shifter itself. And then the delay line also has a corresponding increase in length. That the overall insertion loss going from a 1-section to a 3-section is 2.3 times higher. Going to this border bandwidth phase shifter. Again, this is one of the penalties they need to get paid in order to get bandwidth. Anytime that you have a distributed circuit or distributed element or distributed transformer, like you have in either hybrids or phase shifters, that additional circuit length is just going to increase insertion loss.
Okay, well, excellent information, Shaun, as usual. Can you summarize?
Absolutely. So basically, anytime that we need to add bandwidth to a design, whether it's a hybrid or a phase shifter, there's always a penalty to be paid. The examples that I went through here today really are the 90-degree hybrid and the Schiffman phase shifter. Power dividers and directional couplers also have a similar penalty to be paid. With regard to circuit length versus insertion loss and all of those sorts of parameters. Understand that by adding bandwidth, there will be a penalty to be paid if there's going to be realized in a distributed circuit, like a strip line or a microstrip sort of device. Most of what we talked about here was insertion loss. However, every time you start adding bandwidth, there are other parameters that also begin to get degrade. such as VSWR, isolation, and directivity. In addition to that, anytime you start adding length to line, since the physical length is longer, they become more prone to drift over temperature and all those sorts of performance parameters. So we have to be careful with those as well.
Okay. And you had mentioned earlier about some Quantic TRM differentiators. Can you explain?
Sure. A big part of what Quantic TRM is about is we like to work with our customers to make sure that really what our customers end up with is the best solution for their customer, and which is very often what we talk about just today here is go through these trade-offs in detail and discuss really what is the best performance for the system, what's the best way to physically realize those circuits. It's not just a matter of having a 9-degree hybrid that covers the bandwidth. It's understanding what are the trades that are going to happen. What is that increased insertion loss going to do to your noise figure, and any other parameter that happens to come up. Go through, discuss discuss those parameters with you to make sure that really we know exactly what's going to happen when the system actually finally gets built. As a result of those sorts of understandings, we do go through some very careful selection of materials, the way we approach the design, the way we do our packaging, and then of course the testing that we supply for these components are really designed to make sure that our customers get what they need so that they can be successful.
Okay, well, terrific. And I think we have time for at least one question. And the question I have here is that you focused on amplitude balance today. Are there other parameters in which trade-offs need to be made with respect to bandwidth?
Absolutely, and I hinted at this very quickly. The biggest trade-off really needs to be made when you get into these multi-section sort of transformers, in addition to amplitude and balance, is directivity or isolation. Those are really the biggest parameters that tend to suffer when we start cascading transformers together. Every time that there is a step discontinuity, and every time that we add a section, there is a step discontinuity, there is a small reflection that happens at that interface. What that small reflection does is it affects the even and odd mode velocity propagation of that circuit, which has a direct one-to-one correlation on how well currents cancel and create isolation. So one very major thing that happens is that as you add bandwidth, very often the directivity or the selectivity of how well it rejects signals begins to degrade. So it is one of those trade-offs that need to be made. It's a little less obvious as we add bandwidth, but it is something that we do have to keep in mind. And if we do need a very high performance part that has good directivity and good isolation, very often the way that we get around that is to go through and to narrow the bandwidth so we can help maintain fewer discontinuities in the circuit from a design standpoint, and therefore increase the overall performance both as far as directivity and VSWR. But directivity is kind of the canary in the coal mine that kind of flags this degradation of performance first.
Well, thank you again, Shaun, and thank you again to all of you for joining us today. I think that the bullets on your screen say it all. If you are a customer and you have additional questions or would like to speak with one of our engineers, we would love to hear from you. The engineering hotline number is on your screen, 888-677-6877. Obviously, there's no cost associated with these conversations. If you are one of our field sales representatives, then you know your calls are always welcome. And of course, you can contact us through the portal as well. And going forward, our next Tech Talk will be on Tuesday, December 19th, and the topic will be ground-based dividers and combiners. Thank you all. Thanks again, Shaun.